Okay, in this last section, or subsection rather, of the properties of eigenvectors and eigenvalues section, we'll talk about eigenvalues of a Hermitian matrix. Now, what's a Hermitian matrix? That's what I have written back here. A matrix A is Hermitian if and only if the complex conjugate of A transposed is equal to A. So let's give an example. Let's just give a simple 2 by 2 example. If I have 1 and 4 on the diagonal, and I had, for instance, I have 1 minus I and 1 plus I here. Now, if I take the complex conjugate, that will give me, well, 1 and 4 stay the same. Now, if you remember, complex conjugate takes all the pluses of the imaginary parts and turns them to minuses, and changes all the minus imaginary parts to pluses. So I have 1 minus I here and 1 plus I here. Now, if I take the transpose, I'll get, well, that means I flip these two entries here, and I'll get 1, 4, 1 plus I, 1 minus I, which was exactly the same as this here. Now notice the characteristics of this matrix here. The diagonal is real. The off-diagonal entries, if you just look at the real parts, they're symmetric across the diagonal. The imaginary parts you could call anti-symmetric. I have a plus I here and a minus I here. So let me give you another example of a Hermitian matrix. 3 by 3 this time. Now, if I follow the same rule, that means that, as I mentioned, the diagonal should be real. And it can be any real number. I could do 7 minus 5 minus 3. Okay. The off-diagonal elements, the real parts should be symmetric. So let's just write in some numbers. I'll put 2, 1, and 6. Now, if it's a Hermitian, then the real parts would have to be symmetric, 2, 1, and 6. You see that it's the same across the diagonal, 6 and 6, 1 and 1, 2 and 2. But the imaginary parts would have to be anti-symmetric. So I could put minus I here. If there's a minus I there, there would have to be a plus I here. If this was a plus 2I, this would have to be a minus 2I. And I could leave that as 1 and 1. And it would still be Hermitian. All right, so you can kind of see what the pattern is like. Now, a real Hermitian matrix is symmetric. As I mentioned, if you just look at the real parts of these numbers, they're symmetric across the diagonal. So if there's no imaginary part, then the entire matrix would be symmetric. All right, so this is the type of matrix that we're dealing with. This may seem rather specialized and uncommon, but in fact Hermitian matrices are extremely common in engineering, physics, and other applications. Extremely common. All right, so let's go and look to see what our theorem says. And our theorem says that Hermitian matrices have real eigenvalues. Now there's a proof here. I'm going to do it a slightly different way. What I want to do in order to prove it is, so I'll state it first. So as I said, what we're trying to prove is that Hermitian matrices have real eigenvalues. Okay. So to prove this, I want to consider something. So first of all, say suppose A is Hermitian. And let's let x be eigenvector with eigenvalue lambda. So we want to show that lambda is real. Okay, so that's what we're trying to show. We want to show that lambda is real. Okay, so consider the following. Consider x conjugate transpose times A times x. All right, now you might wonder why I'm considering this. Well, we'll see in a minute. All right. So we know that that's equal to x conjugate transpose times ax, but ax is lambda x. So it's x conjugate transpose times lambda x. Now I can bring the lambda out front, so that's equal to lambda times x conjugate transpose times x. Okay. Now on the other hand, if I take the complex conjugate of this, in other words, if I take x conjugate transpose a x, and I take the complex conjugate of this, well, complex conjugates of matrices work the same way they do with numbers. I can take the complex conjugate of these individual factors here. So that's going to be x complex conjugate transpose, and take the complex conjugate of that, and then a complex conjugate, and then x complex conjugate. Now, the two conjugates cancel each other out, so I just get x a transpose, a conjugate x. Oh, I'm sorry, there's still the transpose here. The two complex conjugates cancel each other out, but I still have the transpose. Now, suppose I take the transpose of this. Hang on a second, where am I? Okay. If I take the transpose, now when you take the transpose, we've talked about how you take this product of matrices but take them in the reverse order. AB, so remember that AB transpose equals B transpose A transpose. Now this is for two matrices, but the same thing works for three matrices. So that would give me x conjugate transpose, then A conjugate transpose, and then x transpose transpose, but x transpose transpose is equal to x. So let me move this down. So that would give me, so that's equal to x conjugate transpose, A conjugate transpose, and x. But we know that A conjugate transpose is equal to A, since A is Hermitian. Okay, so this is equal to x conjugate transpose times AX, which is just equal to x conjugate transpose times lambda x, which is equal to lambda times x conjugate transpose x. All right? Now notice, I've got the same thing here and there. Those two things are equal. I ended up with the same thing. This here and this here ended out to be the same thing. What does that tell me? That tells me that this number here, x conjugate transpose AX, if I take its complex conjugate and I take its transpose, then I get the same number. Okay. So I'm getting that so I'm getting that, move it down again. So I'm getting that X conjugate transpose AX, and I take its conjugate transpose, is equal to the same number, X conjugate transpose AX. All right? All right, so this looks kind of complicated, but what are we really saying here? What is this object? What does it look like? Well, X conjugate transpose is the same size as X transpose, and A is n by n, and X is n by 1. So here we have an n by n, here we have an n by 1, and X conjugate transpose is the same size as X transpose, so that's 1 by n. So we have a 1 by n times n by n times n by 1. What size is that? Well, these dimensions match, these dimensions match. The result is going to be a 1 by 1 matrix. So it's just a number. Okay. So this is a number, this is a number. Okay. Now what is the transpose of a number? Well, the transpose of a 1 by 1 matrix is just a 1 by 1 matrix. So in this case, the transpose doesn't really matter. What we've shown is that this number is equal to its complex conjugate. The number is equal to its complex conjugate. The only way that can happen is if the number is real. You can think about it. 1 plus I, well, that's not equal to 1 minus I. Why not? Because it has an imaginary part. Any number which has an imaginary part cannot possibly be equal to its transpose. All right? So the conclusion here is that X transpose, let me just write that intermediate step, that X transpose AX is equal to the complex conjugate of X transpose AX, sorry, X conjugate transpose AX is equal to transpose AX. So that tells me that X conjugate transpose AX must be real. Okay? Now up top here we had an expression for X transpose AX. It was equal to lambda times X conjugate transpose times X. Okay. So that means that lambda times X conjugate transpose times X must be real. Right? But what about X conjugate transpose times X? Well, we can write that out. X, lambda here, X conjugate transpose is going to be a row vector. Now, first I'll write what X is. X is the vector x1 up to xn. X conjugate transpose is going to be x1 conjugate up to xn conjugate. So this shouldn't be lambda equals, it's lambda times this. So it's equal to lambda times this. That's equal to lambda times x1 conjugate x1 plus x2 conjugate x2 plus up to xn conjugate xn. This is the result of what you get when you do this matrix multiplication. Right? You're doing a sum of products. The first product is x1 conjugate x1. Next one's going to be x2 conjugate x2, and so on. Now what about this product here? Let me write this a little bit more neatly. This is going to be x2. These are going to be x2s. And then we'll have xn, xn. This is a number times its complex conjugate. From complex numbers, we know that that's the same as the absolute value of the number squared. So this is equal to lambda times the absolute value of x1 squared plus dot 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 plus absolute value of xn squared. Now this number is certainly greater than 0 if x is not 0. Right? X has several components. If even one of them is not 0, then we'll have a non-zero term in this sum. So we have lambda times a positive number, which must be real. Right? We said that this thing must be real. Now this is a positive number, so that means that lambda also must be real. So just a recap on this proof, we took this quantity x conjugate transpose ax, and we expressed it in terms of lambda. Then we took the conjugate transpose of this quantity and showed it was equal to the same thing. So that means that lambda x transpose conjugate x must be equal to its own conjugate transpose. And then we showed that this part was real, which implied that lambda must also be real. Okay. A little bit long proof the first time, but you get used to this kind of proof. It's very common in linear algebra. Okay. So, you know, first time exposure, it must look quite complicated. The second proof that we have will actually look quite similar. Now you can compare his proof to my proof. If you prefer his proof, you might, because different people have different tastes. All right, the second proof in this section is that Hermitian matrices have orthogonal eigenvectors. What does orthogonal mean? So let me go back here, and again, you can read his proof, or you can take a look at what I'm going to do. So let's say that we have now, we'll do a little bit more complicated situation. Now suppose that x and y are eigenvectors of A with eigenvalues I'll say lambda and mu. Okay, now let's consider, I'm going to consider something similar to what I considered before, but this time I'm going to consider y conjugate transpose times A times x. Okay. Now, we're assuming that A is Hermitian. Okay. Now, what must be true of this? Well, let's do the same. Well, all right, first of all, we know that x is an eigenvector of A with eigenvalue lambda, so this must be equal to y conjugate transpose times AX, which is equal to y conjugate transpose times lambda x, which is equal to lambda times y conjugate transpose x. Okay. Now, on the other hand, we can take the conjugate transpose of this quantity just like we did in the previous case. So now consider the complex conjugate transpose of this quantity, y conjugate transpose AX, and we'll take the conjugate and we'll take the transpose of this. Now the conjugate factors into the separate terms, so that will give me y transpose A conjugate x transpose, x conjugate, sorry, and then we have that transposed. And the transpose gives me the transpose of the individual factors in the reverse order. So that's equal to x conjugate transpose times A conjugate transpose times y. But y transpose, let's say y transpose transpose, we can simplify that as x conjugate transpose A conjugate transpose times y, because y transpose transpose is equal to y. Now, lo and behold, A is Hermitian, so A conjugate transpose is equal to A. So I can write this as A conjugate transpose times A, what did I say, x conjugate transpose times A times y. But AY, remember that y is an eigenvector of A, so this is x conjugate transpose times mu times y. So that's equal to mu times x conjugate transpose times y. All right? All right, now, again, we need to consider what kind of object this is. Just like before, this is a number. This is a number. We're saying that the conjugate transpose of this number is equal to this number. Okay. So let me write that out. So we have shown that the conjugate transpose of how am I going to write this? Well, first of all, I have lambda times y times x. I guess it's y conjugate transpose x, and that was equal to y conjugate transpose times ax. And if you take the conjugate transpose of this, conjugate transpose, conjugate transpose, this is equal to x conjugate x conjugate transpose ay, which is equal to mu times x conjugate transpose y. All right. Now, so what do we have here? The complex conjugate transpose of this quantity is equal to this quantity. Now, as before, this is a number. The transpose of a number is just that number. So we just have that the complex conjugate of this quantity is equal to this quantity. So I can say the complex conjugate of A times y conjugate transpose x is equal to mu times x conjugate transpose y. Now, I can factor this complex conjugate in here because I have the complex conjugate of a product. So I can just take the complex conjugates of the different terms. Lambda complex conjugate, y conjugate transpose x conjugate is equal to mu times x conjugate transpose y. Okay, I can also factor the complex conjugate in here, and so I get x lambda bar times y transpose x conjugate is equal to mu times x conjugate transpose. Okay. Now, since lambda is real, lambda bar is equal to lambda. since lambda is real. We already showed that. Okay. Now, this number here is just equal to the transpose of this number here, but since they're numbers, that means they're equal. So I could write this same thing as x conjugate transpose y, and that's equal to mu times x conjugate transpose y. So what does that tell me? I'm going to write it here to save some space. If I put these both on the same side, I'm going to get lambda minus mu times x conjugate transpose y is equal to 0. I just brought the mu term over to the other side. Now, in order for these to be 0, for this to be 0, the product of two numbers can only be 0 if one factor or the other is not 0. But these are different eigenvalues. Okay. So that means this difference is unequal to 0. So that means that this must be 0. Okay. X conjugate transpose y is equal to 0. That must follow. And that's what orthogonal means. That means that the conjugate transpose of the one vector times the other vector is equal to 0. So my final result is that, so what I have is if x and y are eigenvectors of our Hermitian matrix A, with distinct eigenvalues, then x conjugate transpose y. Now I could also write that as y conjugate transpose x. It's the same thing. It should be equal to 0. And that's what it means that x and y are orthogonal. Now you might wonder why there's such a big deal about this. What's the big deal about x conjugate transpose y? We may see that in later chapters. I can just tell you that it is extremely important, and that orthogonality has something to do with the notion of perpendicularity. If you have two vectors that are orthogonal, in some sense they're completely independent, and you can deal with them completely separately. So that is an important conclusion. And just go back to the chapter and see if there's anything else to do. No, we'll just stop there. I think what you can learn importantly from this demonstration is this technique of taking a quantity and using the eigenvalue property to manipulate it and then draw some conclusions from there. So I'm going to stop there and see you next video.